Hi, everyone. It's a pleasure to be with you this afternoon. My name is Bruce Brotherson, and I work for Volcraft. First off, a friendly reminder to turn your phones off so that they don't interfere with the presentation today. The name of the presentation is Simple Connections Simplified. So everything's going to be simple. We have, and essentially the presentation is broken into two parts. The first part is going to be information on how to attach joist and deck. And then the second part is going to be about attaching other things to the joist and deck. This webinar or this presentation is sponsored by the Steel Joist Institute, and the Steel Joist Institute has been around for 90 years, and they're made up of 9 companies with 31 manufacturing plants in Canada and the United States and Mexico, with an annual capacity of about 150 million tons. And if you'd like to learn more, you can go to the Steel Joist Institute website or visit us at our booth, which is right across from the AISC booth, and the booth number is 818. You can see what the code is, 4484. And our presenters today is going to be Tim Halderman. He's a PE and an SE, and the Director of Engineering for Can-Am US. And Tim also serves as the Engineering Practice Committee Chairman for the SJI. Our second speaker is going to be Jeff Martin, who's a PE, and is the Supervisor for Deck Development for the Volcraft Verco Group Technical Services. And with that, we'll turn the time over to Tim.
Thank you, Bruce. So I'll start with the topics surrounding joists, and then Jeff will take over and take on the topics related to deck. My part will be in 6 sections, so some discussion of joists to support connections, joist girder to support, bridging connections, lateral load connections, structural elements that connect to joist, and also trade elements that may be connected to the joist. So structurally, a welded joist seat to support connection is adequate, but OSHA requires bolts in certain cases, and those would be tie joists, which would be the bar joist that goes column to column, and also spans that are over 40 feet on steel supports. The bolts and slotted holes may not provide adequate lateral support to the compression cord or flange of the supporting member, and so therefore, hence, bolted and welded joist end anchorage is common or the industry norm when we're on steel bearings and we're over 40 feet long. So this graphic shows just the typical bolted and welded joist seat sitting on a support that looks like a girder top cord. And if we look at that seat in detail and the forces that we have going on there, the gravity load is the easy one. The joist is underslung, and it's a very simple connection. It's basically in bearing. But then our bolts and welds are for the directions and or the forces in other directions. We're likely to have an uplift interaction if we're on a roof, pulling up, and basically the bolts are going to help resist that, and it's sort of a prying action or holding the seat down to resist that uplift interaction. Then we can have some lateral forces in 2 directions. We could have a load that's axial along the length of the joist. We could also have a rollover force where we're taking some diaphragm force down through the seat. So those are resisted in various ways. The rollover gets a little bit complex because we're basically bearing on one side and pulling up like the uplift reaction on the other side. But when we're using bolts and welds, the thing to know is that the bolts are basically there for the uplift interaction, and the weld is there to take lateral loads, but also beyond all these loads stated here, to provide lateral support to the member underneath. So it's typical in the joist industry to have a slot in that bearing seat, and that is not an AISC slip critical connection. So this chart just summarizes the SJI requirements for bearing connections and end anchorages, and I'm going to focus on joists right now. Recent changes have increased the length of the welds, the minimum lengths, and that's so that we can gauge more of the seat to resist for prying action and for uplift resistance. So for all of the K-series joists, the minimum weld is 1/8 by 2.5 inches. That is a little bit of an increase in our latest specification. For LH02 to 06, These are now kind of carved out, and recognizing that typically those aren't any heavier than a K-series joist. So we've got sort of an intermediate step of a 3/16 inch weld, also 2.5 inches long. Then when we get into LH series joist and DLH series joists, we're getting into a 1/4 inch thick weld, but still 2.5 inches long. And then the very large DLH joists, numbers 18 through 25, these are getting really big, heavy capacities, long spans. We're up to a 1/4 by 4 inch weld. On the other column here, we summarize the bolting requirements, and that starts with a 1/2 inch bolt, and a nominal A307 bolt is adequate for K-series and those smallest LH. Then we graduate to a 3/4 inch bolt for the typical LHs, and then for the very large ones, still 3/4, but we need to go to an A325. So a suggestion here relative to simplification is that while we have that intermediate step for the LHO2 to LHO6, it may be easiest to just use the same end anchorage requirements and combine them with the 07 through 17. So if we had a mix, let's say with some LHO05s and LHO8s in the same job, it could be a little bit cumbersome to start to differentiate these requirements, and it's probably simplest to just stick with the more typical LH requirements, which would be the 1/4 inch weld and the 3/4 inch diameter bolt. Here's a detail of a typical joist sitting on a joist girder and a blow up of that connection we've already seen. An important thing to note, or a way to keep things simple, is to remember that the joist bearing seat bolts only need to be snug tight. So the AISC definition for that is like the ordinary man with the ordinary pressure with the ordinary wrench kind of deal, but there's no need to use a fully tensioned bolt. And in fact, it would be difficult to do that. The typical joist girder web member configuration limit access for the use of a power tool if you were to try to tension all those bolts. So we can see this is just a picture of one cord with 2 holes there ready to receive a joist that would be sitting on top, and a couple of double angle web members coming in. So there's adequate clearance there to get the bolt in there, get a nut on it, maybe get a wrench on there, but a power tool is not going to have access to that. I mentioned the OSHA rule, and just want to touch on that again for a couple of key things. So this is the nitty gritty, and I'm not going to read all this language here, but I'll point a couple things. It says that it shall be fabricated to allow for field bolting. So it doesn't say that it must be field bolted. It just says allow for it. And then this clause, they shall be full bolted unless constructability does not allow. Well, that seems to me to be a pretty large loophole, and it's not quite clear what that means. So realistically, while bolted condition must be detailed for us to meet the OSHA requirements, it may or may not be actually used. So that creates a little bit of a concern then, in that where a joist seat's been detailed for a bolted connection, and if for any reason the bolt isn't utilized, then we have a concern about that empty slot and some weakness there if we're just welding, in particular if we're welding on this little ribbon of steel adjacent to the slot, then we're pretty weak. So what this slide indicates is that we want to place a weld inside that empty slot, and depending on how long that slot is, we may not be able to get the full required weld length, so then we can supplement that by putting some weld on the edges of the seat in addition, but we want to put that away from the slot location. So that's sort of a 3D view of that. This next slide just shows the same thing in terms of a typical note that might appear on the joist placement plans, and again, it's just directing that bolt's not present. Weld inside the slot first. If more weld length's required, then finish up the weld or complete the weld by doing it out there on the toe. Another topic related to joist sitting as supports would be the case of a skewed bearing and a really tight angle for the joist intersecting the supporting beam. So we can see a joist here and another one on the other side. I guess it doesn't have a label on it, but in the red circle where that comes together. So it's really tough to get a good working point up over the beam and get a proper support when an angle gets really tight. And the guideline here indicates that if that angle between the beam and between the joist and its supporting beam is less than 15 degrees, then the suggestion is to use some alternates to avoid a connection that's going to get eccentric. And the next couple of slides show some of those alternates. First and probably simplest choice would be to just skew that that joist. So that's the location shown in red there, and just run it the full length and put it all the way over to this other supporting beam. Now, in general, out in the middle of a bay, if we start skewing some joists, we can create some real complications for the deck layout and where the deck is going to lap. But in this case, it only makes sense that the deck is going to be terminating, or the sheet's going to end on the skewed beam, and the lap's probably going to be a couple of joist spaces back. So there's not really going to be any problem relative to a deck joint and skewing that one joist. So that cleans this up pretty nicely and easily. It's interesting too in that even though this might be a little bit of a longer joist, arguably this one's is easier for the joist manufacturer to do because it's probably going to be a lot like its neighbor instead of building a completely different joist at a different depth for a shorter span coming to that skewed beam. Another alternative, though, would be to specify a header, which would be a little piece of auxiliary steel that a joist manufacturer can supply to create a bearing that runs from the adjacent joist over to the beam and to stop the joist here. It could have a little topcourt extension to it to continue the deck support out here, but the idea would be the primary support and the load is now transferred from the header to that skewed beam at a much more favorable angle. What we use inside our office, just as a way to dimension this or where we might put that header, would be to figure nominally 1 foot from the intersection of the skewed beam over to where the joist would sit. So, hey, there's some economy in putting that somewhere, keeping it near the end of that header, but we don't want to get it too tight to the end to have trouble making that connection. All right, the next couple of topics are with regard to joist girders to support. So this is the same table we saw a moment ago, but now I want to focus on what it says for the joist girders. And we see that there's a differentiation made depending on the self-weight of the girder, or basically whether we have a light girder or a heavy girder. So the footnote, not sure how well you can read that, but it states that joist girders with a self-weight greater than 50 PLF would fall into this the bottom row there, which gets us into a 1/4 by 4 inch weld as a minimum, and then 2 3/4 inch bolts, A325 grade though, if we're in a heavier joist girder. The line above would be girders that are 50 PLF or less. So a suggestion here for some simplification would be, in terms of bolts, it's common for 3/4 inch bolts out at the job site to all be A325 anyway, and there's not a big expense in terms of A325 versus A307. So the suggestion would be really, even though the minimum is that A307 bolt, the suggestion would be just use A325 bolts for all girder bolted connections, and that way we met the SGI requirements and kept it simple. If it's the weld length, the erector might not like to be welding 4 inches if only 2.5 inches are required. But my suggestion there would be, if you have a mix of girders, some of them are lighter, some of them are heavier, just make it the 4-inch weld throughout. That keeps things simpler. If the girders were all small and relatively light, maybe the maximum girder span was only 30 feet long on the project, then the smaller or shorter weld length would certainly be appropriate and gain some economy. So how do we know what those girders might weigh? Just a reminder that the SGI publications have weight tables that give an indication of the self-weight of the joist girder. So it starts at the span and what the kip loading is in either ASD or factored LRFD, and then a weight in pounds per lineal foot. So the red lines there just kind of show, I added those to show where that stepping point is above and below the 50 PLF. An additional note to make relative to joist girders to supports, what we have here is a typical joist girder seat caught in the wild before it was put into a girder. So it's just 2 angles back to back that'll slide in the gap to make the seat. So the note here is just to be aware that it's entirely possible that the uplift reaction for joist girder, if the joist girder is fairly long and if you're in an area where the wind loads are pretty severe and you've got a lot of net uplift, they could exceed the capacity of those minimum SGI bolts. So the requirement for 2 bolts, 3/4 inch round, if they're A325s, we can develop about 24 kips of capacity when considering the prying action, just taking those seat angles just as we see them, and then if we just took the full tensile capacity of that pair of bolts, it's about 39 kips. So if we stiffen this up or got rid of the prying effects and stiffen it, ultimately we could exceed just the tensile capacity of the bolts. So that's certainly something to watch out for. There's a couple different options. One would be, it would be possible to justify or take a closer look at a joist girder as a main wind force resisting system instead of components and cladding. So typically the end reaction we arrive at is taking the components and cladding forces and adding them all up, but that may be a little bit conservative. Other options would be a larger diameter bolt, higher graded bolt, or in a worst case scenario, the possibility of going to a 4-bolt scenario for that anchorage. Next couple of slides talk about some topics relative to bridging connections. This is something new in the latest edition of the SGI publication. Maybe a little bit hard to read there, but it's the bridging chart. But where in the past SGI just gave the force requirements for the bridging, now they're specifically indicating the weld sizes. So we start with a very small nominal 1/8 by 1 inch weld, which is good all the way up to an LH15 joist. So the vast majority of joists, that 1/8 by 1 inch weld is plenty. But as we get to bigger, deeper long spans, then we need a bigger weld, and that's specified here. Now, some flexibility might be in order, or again, this is giving one option for meeting the requirements. So we see on the bottom there, the weld is 1/8 by 3. Well, if the bridging angle is only a 2 by 2 or 2.5 inch angle, then it may be desirable to use a thicker weld and shorten the length, or it may be possible to weld on both sides of that member, but those welds get longer. The next chart is unchanged from SGI, but just making people aware that it's in there to indicate the bridging bolt requirements when it's bolted bridging. That's found in the Code of Standard Practice. And a 3/8 inch A307 bolt is good for all of K series and the LH series up through an LH12. So that covers the vast majority of what we do. But again, as we get to bigger, deeper, heavier, long span joists, the bolt diameters go up, and ultimately the grade goes up a little bit as well. An important note about diagonal bridging and its connections is that the diagonal bridging must be connected at the intersection. So the diagonal bridging is resisting a compressive axial load, and the design presumes a connection at the center of the X and takes an unbraced length from that center point to the connection of the cord. So that center connection really doesn't matter. Typically if it's bolted bridging, it's going to be bolted at the center as well. If it's welded, it's going to be welded at the center. But really, it doesn't matter how that's made as long as they're joined at the center. That's what's important. And a quick note about horizontal bridging. These are a couple of field pictures, and while the bridging weld requirements are often minimal, and I showed a couple slides ago that it was only 1/8 by 1 inch for a lot of cases, some care needs to be taken because the material is typically pretty thin. So the erector is not careful in making the welds, you can get a bit of a mess. We can see a burn hole there, and there's a closer up view of it, and the welds aren't so great there in terms of where we have a lap from one piece of horizontal bridging to the other. So we don't have to develop a lot of force, but that doesn't mean that they shouldn't exercise a little bit of care in making those welds. Next series of topics relate to lateral load connections. So if the joist and joist girders are part of the lateral system and how they may be involved or connected to that. The first point to make is that top cord axial loads and end moments should be transmitted directly via tie plates or tie angles. The eccentricity of horizontal forces transferred through the bearing seats is then avoided. So the load path for an axial load, whether that is from a moment couple or direct axial load or collector element, is denoted by F, and that's traveling along the neutral axis of the top cord. So if we don't have any other means to transfer that, we've got the eccentricity represented by E that develops a moment as we take that force down to the base of the seat. Obviously, the severity of that is a function of the depth of the seat in addition to the magnitude of the force F, but that becomes cumbersome pretty quickly. So if that force is relatively small, there's options to take that through the seat. So if we were talking 2 kips, 3 kips, 5 kips, 10 kips, something like that, we could take through the seat. But if we start to get 20, 30, 40, 50 or on up kip loads as far as an axial load, we definitely need another means or a load path to transfer that. So one One good option would be a tie plate. It creates an effective axial load path. And typically, the disruption to the deck above is minimal, or it's not a problem to lay the deck over that weld plate, if that's a 3/8, quarter, half-inch thick, something like that. Hopefully Jeff won't correct me on that later. Another option, though, would be to use a pair of triangles. Those triangles can be tucked below the outstanding leg of the top chord, and then the horizontal legs get pointed in towards the joist access, so that leaves some clearance for the web members, and clearance for bolt heads if that was a bolted connection along column lines, and we have a detail that looks like this. So to keep things simple, tie plates should be narrow enough to allow downward rather than overhead welds. So for greater capacity, though, there's also an option where the nominal 1-inch chord seat gap can be held clear for a plate to be placed in the gap. So the details we see down below, the one to the far left, the plate is wider than the top of the top chord, so that's going to end up being an overhead weld in the field, so that's not desirable. The simplest one would be the one in the middle. If we have a plate that's narrower than the width of the top chord, we've got a nice downhand weld, and that's easy to make. If we can't develop enough capacity on that plate, then an option is to put something in the gap. And that nominal gap is 1 inch thick, so it's easy to put a 7/8 or a 1-inch plate in there that can develop quite a bit of capacity. Another part of the lateral load system may be the diaphragm edge angle, and if that's attached to the top of the top chord, as we see in this detail, we got a weld symbol that doesn't show a size there, but that needs to be given a little bit of thought, or to keep things simple, we don't want to get too carried away with what that weld is and have that start to influence or problem for the joist top chord to receive that weld. So as we see on the next slide, here are some practical limits and guidance for fillet welds. So as the diagram shows, typically the maximum fillet weld we're going to be able to develop on one of the toes is equal to the thickness of that angle. So whatever the angle thickness is, that's the maximum fillet weld we could put here at the seat or at the edge of the top chord. For this one up here, the practical limit is 4/3 of the thickness of the material, because we could put a nice big fillet weld on there, but then the controlling case would be a shear tear out of that chord material if we're trying to develop a weld that's significantly thicker than the underlying material. So some guidelines then are practical limits. These are a little bit conservative, but to keep you out of trouble would be to figure 1/8 inch as a good fillet weld size for K series joists, 3/16 inch thick for LH series joists, and then 1/4 inch thick for joist girders. And that's for welding at the toe, or an assumption about sort of minimum chord thickness. If we're welding at the leg of a chord or an angle, then that 4/3 of these limits would be appropriate, and that's, again, to keep from having a shear tear-out issue. All right, at this time, we will pause to do an assessment question. This is incredibly simple, but we're required to do this. So the question here, make sure everybody's still paying some degree of attention. Welded connections to and from steel joists are simplest if A, the weld is as thick as possible to minimize length, or B, the weld is positioned such that it is done overhead, C, the weld is lengthened as required to limit thickness, or D, if a multi-pass weld can be utilized. So think fast. The answer is C, correct. So welded connections are simplest if the weld length can be lengthened, the length can be long enough to limit the thickness, and longer, thinner fillet welds to seats and chords will prevent the weld size from controlling the seat or chord thickness, or in the case of like that prying action uplift, we're going to engage more length of material to resist that force. Another couple of slides here in the topic relative to lateral load is that to transfer large shear forces from deck to structural members and avoid a large seat rollover forces, a simple shear collector can be used. So it's possible to design that seat and to take a rollover force, and if we had to, we could put stiffeners in it, but that's not real simple. And another concern besides the manufacturing the joist is developing enough of a connection capacity up at the top to deliver all that force there in the first place. So if the order of magnitude of a rollover force is going to get large along a significant collector line, let's say we're 5 kips or more per joist, then a shear collector is a better option. This example shows a K-series joist where a 2.5-inch HSS tube steel works very well, matches the joist seat, and can be placed in between the joists to take care of the shear collection. The next slide just shows something similar for LH, and what's suggested or shown here is a C5 section to accomplish the same thing and match a nominal 5-inch deep LH joist. Although one word of caution and a point about keeping things simple is that you want to have some landing area. The whole point of this is that we got to get some weld from the deck to the shear collector, or we're not doing anything. So it may be that a 5-inch HSS is a better idea, because we got a better chance of hitting that, or we will hit that with a flute. If we've got that C5 by 6.7, we've got to be a lot more careful to make sure that we're actually going to get the low deck flute on it and be able to accomplish those welds. So once the joist girders, and bridging are installed, that's the primary connections to complete that framework, but the connection work may still not be complete because we may have some other things going on. So first we'll talk about some structural elements that might be connected to joists. For structural members, perpendicular joists, such as an angle collector element, simply cope the angle and bear it on the top of the top chord. So instead of trying to make a bolted connection or frame that into that chord angle somehow, the simplest approach here is just here's the top view, there's a profile view, is just to notch that angle so they can just sit on top of the top chord. So if this is sort of a little drag line, maybe near a wind column or something like that, to distribute some force in the deck, and we've just got a small horizontal load, this is going to be the simplest connection. Here's another variation off of that. It's a similar approach. This one happened to be using an HSS member as that little drag element, but what they did is put a plate on top of the HSS member, and that way, again, that we don't have to make a connection into the chord angle directly. We just, that plate runs on top of the top chord, and that's the connection that we've got. The next option, we've got a more significant load or getting into some vertical load and a concern about that cope tab being enough, or maybe we have another structural element like an HSS or a little W6 beam or something like that would be a hanger angle. Not sure how well that shows up, but the idea is to just butt an angle to the end of that member and just let that rest on top of the top chord. So that's the simplest way to make a connection like that. That angle for that hanger doesn't necessarily need to match the depth of the element coming in. So if the force is small and that's a W6 or W8, hey, the angle could probably be a 4x4 angle and just be attached up at the top, and that's going to be fine. The detail that I show over here to the right happens to use a joist sub as an outrigger, and so this is interesting because there's a couple different options here, but it's left a little bit unclear as to what should happen here. So it's a little bit hard to see, but trust me, even if I blew this up, you wouldn't quite know what's happening here. It just sort of shows the end of that outrigger coming in and sort of morphing into that top chord. So it's not clear where the intent there was that would somehow be coped to fit around that chord angle, or another option might be to just sort of tuck it below that top chord angle. But if we're tucking it below that top chord angle, then we've got a little elevation issue equal to the thickness of that top chord, and depending how long the cantilever is, that could start to affect the elevation out of the cantilever portion of it. So left to their own devices, a detail like that, it's likely that it's just going to be tucked underneath and let whatever happens to the elevation happen. If that's okay, that's fine. For sure, though, it's not economical or simple to suggest that this should somehow be field coped to fit. So we want to avoid that sort of thing, and specifying or showing a detail with that end hanger angle is much better than, again, a cope to fit type of situation. If we get into a larger vertical wide flange beam end reaction and connection to a joist, then a shear tab plate could be provided on the joist chord. So this is an example where it was a very large long span joist, probably 6x6 chord angles, and we can see a little shear tab plate just put into the chord and with a couple of holes in it. So that's something that can be done either by the joist manufacturer or potentially be done in the field. If the reaction gets, if we add the condition of a wide flange beam going to a joist girder instead of to a joist, then the simplest connection would be if that can be a seated connection, kind of just like the joists are, and be an underslung sort of connection to be coped out. So that's what this detail is showing, is that wide flange being coped to sit on top. Generally that can work. Obviously a check needs to be made that after the cope there isn't too much shear at that critical section on the beam. But if the interaction isn't too big, then this is going to be the simplest way to connect a wide flange into a joist girder framing system. If there's a more significant beam interaction, then a full depth connection plate or angle can be provided, and that could be shop or field installed. So what we see here is this is calling for an angle 5x5. It's running from the top cord to the bottom cord. It functions kind of like a shear tab connection would coming off a column. So we've got a single line of bolts and the beam that comes to frame into that. This particular detail has a field weld symbol on it to be done in the field. There's some pros and cons either way. Obviously, a connection of this type has to be coordinated with the joist manufacturer, though, because there's certainly, we wouldn't be doing this unless there was a load of significance that needs to be considered in the joist design. And then while a lot of joists are built with the web inside, we don't necessarily know for sure whether all the web would be inside, and we would have to make sure that we don't have webs on the outside that could conflict with putting that angle in place in the field. So since the joist manufacturer is going to have to consider the load, going to have to think about where this angle is and whether it's potentially interfering with any web members, yes, it'll cost some more, but it's not prohibitive in terms of them making that connection or shop installing it, because there's some work to be done there anyway. So this is an example of a beam connection, and in this case, maybe a little hard to see the holes there. And this is a joist before it was installed, so it's laying on top of another one. But basically what we've got is a big, huge, long span joist with a very deep joist, and that's a vertical member. And in this case, a wide flange beam needed to be connected at mid-height of this deep long span joist. So we've beefed up those vertical angles and put holes in the outstanding leg to accommodate that beam connection at mid-height of that big long span joist. This next picture shows the possibility of bearing a structural element across the top of the bottom cord angles. And while that seems like a pretty simple connection, hey, it can sit there, and from a gravity load standpoint, it's concentric and pretty easy to put it there. I really kind of recommend against this approach, because it can be a real problem to coordinate the web member of the joist around that. So, hey, we got to maintain, avoid eccentricities in the construction of the joist and bring all our web members to a point. And if there was one place along the span, it might be possible to align them all, but where this gets out of hand is, let's say it was an auditorium or something like that, and there's a lot of different hangers for a catwalk system or something that goes all over the place. You start to get a bunch of these along the length of one span of joist. You get a real problem in trying to coordinate that and get some web members to fit around it. A quick note to make here, to keep things simple and simple span, is that if there's a wind column connection at the mid span of a bottom cord, then we're not counting that as a support. If the intent is for that edge girder or edge joist to span a full distance column to column, and the idea of the intermediate column is simply to be a wind column, then we're not designing it as a support, either the column or the girder. So what we want, what's shown in the red circle there, is the fact that it's calling out a vertically slotted hole, so that joist girder can perform as a simply supported member between the primary columns, and it can deflect, and then the bolts will bear in the lateral direction to take the wind, which is the purpose of that wind column. Joists simply cannot take out-of-plane torsional loads. So this example has a wind screen, but really it applies to any condition where we could get an out-of-plane torsional load. For a wind screen or something like this, it's best to extend the post and attach to both the top and bottom cord, and then we resolve the overturning moment with bracing members below the plane of the roof. So it's also possible to put some sort of a bracing member above the plane of the roof, but depending on if this is making a rooftop unit enclosure, then that limits the space available to set the units, and there's also more deck penetrations to have to deal with. So running it down to the bottom chord and putting that framing to resolve out that lateral overturning moment below the deck is the best course of action. And where we have a windscreen post that isn't braced above the roof and the screen is perpendicular to the joist, it's also still best there to extend the post and attach to both the top and bottom chord. And that's simpler than just putting this post on the top of the top chord and developing a large local moment at the top chord from the overturning. So best to resolve that overturning moment into a couple that goes to the top and bottom chord. We can see out here where it's broken up in an axial load at the top and bottom from resolving that overturning moment couple. All right, the next batch of slides talk about various trade elements connected to the joist. So those last things, could be for some hanger or something that's arguably from one of the trades, but the spirit of that was more structural elements. And now we're talking about the other building trades, MEP stuff that's going to come along and attach things. So the first topic to discuss here that's important is to understand sort of and establish what the rules of the road are, so to speak, relative to attachment points. So joist is a truss, and a truss by nature has all axially loaded members. We are checking top chords for a combined bending and axial load, a local bending moment from a uniform load. But if we put a larger point load on there, the implications of that in terms of the local bending are much more severe than just the uniform load. So we have a concern about a point load that would be away from a panel point on the top chord, even though we've designed for some bending. And the bottom chord, that's typically just an axial loaded member. It's got an axial load from tension when it's gravity loaded, and when it's uplifted, it's an axial compressive load, but typically there's not any bending inherently in the design there. So if we have a point load that would be away from a panel point and introduce bending, that becomes a concern. So this is the typical detail that we see all over the place on joist drawings, which is suggesting to the erector, if you can, hang the stuff at panel points, or that by default, if you're away from a panel point, you need to think about adding this additional strut member, or in essence, you're creating your own panel point to transfer the load to a panel point on the adjacent chord. There is an exception to that, and it's an important one, and it's helpful. And what SGI allows as an exception is for loads that meet certain conditions, and I'll read this. For nominal concentrated loads between panel points, which have been accounted for in the specified uniform design loads, a strut to transfer the load to a panel point on the opposite chord shall not be required, provided the sum of the concentrated loads within a chord panel does not exceed 100 pounds and the attachments are concentric to the chord. So there's a whole bunch of stuff there, but the main thing is that SGI did research and determined that, hey, for a little bit of load, yes, the chords can take some bending, and that little bit of load is defined as 100 pounds. Now there's a couple other strings attached to that. The 100 pounds, the caveat is that it should be concentric to the chord. Also, that's a limit of either one load or a summation of loads within one panel. So that's not, well, as long as the loads are less than 100 pounds, I could put 5 of them in one panel. That would certainly overstress it. So the idea is that the sum within any one panel not exceeding 100 pounds. And then the part about already being kind of in the design, the spirit of this, and we'll see that again in a couple of slides later, is that that the load was already accounted for in uniform design loads. So there was a 5 PSF miscellaneous and mechanical, or 2 PSF for sprinkler branch lines. So in a PSF uniform load basis, with the loads already accounted for, it's just that the load isn't really being applied uniformly. It's being that 2 PSF or 5 PSF is being accumulated over an area and now put on at one discrete point. That's what this is alluding to or speaking to. So that's the basic provision that's there all the time as an exception from SGI. There are also some other design capabilities and possibilities that really help for trade elements, and those are add loads and bend check loads, or a combination of both. So an add load is a single vertical concentrated load. It's basically a traveling load that it could occur at any one panel point, and it's adding on top of the uniform loads and other gravity loads, adding to the overall moment and shear. A bend check load is a vertical concentrated load used to design locally within the panel for bending. So it's common to specify maybe the same magnitude for both. If there's an extra 500 pounds as an add load, that's going to take care of the global moment in shear. And then also saying it's a 500 pounds as bend check load will have us check it in the local bending as well. And the next two slides just show that a little more clearly, that again, an add load, the idea is it's going to be it's a traveling load at any panel point. The magnitude needs to be specified in pounds. The load could be specified to be at the top chord or the bottom chord, or to be at either. An add load is still just traveling or marching across from panel point to panel point. So off panel point loads would still need to have field installed webs. I think a good example for an add load case might be a sprinkler main or some sort of pipe that's running parallel to the joist. Well, it's running parallel to the joist. The installer should have some latitude to put that wrap around the pipe and locate that at a panel point. So basically, if he takes a little care, he should be able to hit panel points. If he wants to optimize and save one hanger and go at exactly 15 foot on center, regardless of panel points, then he can add a strut, but he certainly had an option in hand to avoid that. In other cases, though, it may make sense that to have some design for local bending and to avoid the need for some of the added struts. So a bend check load will check that localized bending if that load P is in the middle of a panel. The example shown here is, hey, if there's a 2 PSF allowance for sprinkler branch lines, and that may accumulate and create a load in excess, maybe in excess of 100 pounds within a given panel, then specifying bend check load will make sure that we're checking for some bending within those panels. Another important point to make about trade elements that get connected to joists is that the field drilling of joist members should not happen to attach anything. The detail here is specifically showing a hole at the bottom chord. That's probably the more critical element because it's a tension member, and if we're taking away area, we are definitely diminishing capacity. But really, we don't want to see field drilling. Obviously, in the top chord after the joist installed, not such a good idea to go drilling through the top chord and through the deck and potentially creating a little roofing issue later on. And the web members are typically smaller members. There's definitely going to be implications if we lose some of the area on those. So next slide shows some various details for different trade elements being hung. So this first one is a very simple and concentric hanger. So if the load is less than 100 pounds, or we had a bend check load and we've checked for bending, then we could hang this in the middle of the panel. And this little detail just shows a threaded rod going through the chord gap, and we're hanging the pipe that way. So that's a great, simple, concentric hanger connection. Another option is to use auxiliary steel, and maybe the item being hung is actually placed between two joists. These details happen to use unistrut. That's a great material to potentially use for that auxiliary framing. So this just shows an auxiliary hanger example where it goes across the bottom of the bottom chords. Next slide is just a different view, a cross-section view, shows how that would be going from joist to joist, and then whatever needs to hang would be attached to those unistrut members. And this shows the blown up detail of that actually being attached to the bottom chord. So that is a good attachment, and we do not have concerns about being eccentric with that type of a connection. Next couple of slides just kind of show the same concept, but that the auxiliary steel hanger could be placed across the top of the top chords. Now, I said earlier that I was kind of advising against that for a structural element. Well, a structural element is something probably that has a very discrete location that needs to be maintained, which would mean we have to work the webs around it. It's different when we come to the trades, because now the joist is already built and they're going to put those trades in. They may have some latitude of where they put them, or could work around the existing panel points. So here, no problem with running that auxiliary steel across the top of the toes of the bottom chord. And again, that's a good way to make a concentric connection. Again, we've got just a cross-section view, shows that going across. That's like two unistrut channels just stacked on top of each other to make a combined section. And this shows a detail of that connection being made. Again, bolting through the chord gap. that unistrut allows this sort of plate washer to kind of tuck in there and bolt it within the channel. This is a section for a beam clamp hanger, and for a small little pipe or branch line or something like that. This is not concentric, but it's certainly common within the industry, and I would say it could be used with discretion for very small loads. So in this case, this is a cut from an engineer record drawings. So this is good because he's putting some specific parameters on there in terms of a limit on the diameter of the pipe and a limit on the spacing, so it's about how much load would be there. But for sure, if we say that SGI is nominally allowing 100 pounds in any given panel, provided it's concentric in those other conditions, we wouldn't want to see anywhere close to 100 pounds in this condition, because it's certainly only going to one chord angle at that point where it's being loaded, and there's also potential, depending on how good a job they do of sliding that clamp on there, of creating a little bit of a torsional effect as well. So to me, this sort of thing needs to be several magnitudes, the limit on it needs to be several magnitudes smaller than that nominal 100 pounds, or if there was a bend check load specified, that a 200 pound or 400 pound bend check load would not give license to say that this would be adequate up to that magnitude. It might be okay for some small percentage or portion of that. Here's another similar thing, although a little bit different. So this is a trapeze detail, and again, it may be a little bit hard to see there, but that's got the beam clamp again. But this is maybe a little bit better than the last one, because one of the things that will happen here is we're still only connecting to one chord angle, so we still got to use some discretion, and we don't want to run up to the maximum limit of our bending load. But because we've got two of these, and we've got a stiff element in between here that has to be stiff enough to take bending, that's sort of resisting any tendency to have any torsional effects, because those tend to be equal and offsetting. So this slide just shows a very simple connection for a light hanger. So if we're talking now about lighting or a piece of ductwork, a wrapped wire for a very lightweight miscellaneous hanger, that's a good idea. So we see a detail there of a wire just kind of wrapped around, except in this case it's actually hung from the bridging. So we see the joist running sort of east-west, and the bridging running up and down, and that's actually done in the bridging. So using just wrapping a wire like that is a fine simple gravity connection, which is fine, but that should be from a bottom cord and not from a piece of bridging. So that concludes my topics relative to joists and connections. This is picture there is the latest Steel Joist Institute catalog. It's the 44th edition, which is available. And if you have not gotten a hold of that, I would encourage you to do so. And with that, I'm going to turn it over to Jeff. Thank you.
Thank you, Tim. Oh, sorry. So now that we've got the joist up, the next step in the process is the next step in the construction process is to put the roof down. So we're going to look at some of the issues that impact the selection of deck connections. Understanding the issues is going to, I hope, help simplify the selection process. Understanding some of the resources available will also hopefully do that as well. Start with a summary of some of the connections or the topics that we're going to cover. We'll start first by looking at the different connection types. So what kind of connections are we looking at? Well, here we've illustrated the different connections that attach the deck. The this high-end pointer. Anyway, the perpendicular support connections, the parallel edge fasteners or edge connections, which are typically assumed to be the same type of fastener, the side lap fasteners that connect the two deck sheets together in the middle. I didn't illustrate hanging connections here, but we will talk about those separately. This image is basically describing roof deck. The connections we'll talk about will be equally applicable to composite or floor decks as well. Start by looking at support connections. Three basic types of support connections: welds, power actuated fasteners, self-drilling screws. Short and sweet. The welds are the strongest, but they're the most expensive and most difficult to put in. Power action fasteners go in 5 or 6 times faster, have slightly less strength, but not enough that you can't get to essentially the same kind of capacities that you can with welded systems. Self-drilling screws are obviously slower, but they may be the only choice if you're looking at cold form framing or if you're looking at some of the thinner chord angles on joist. Deck installers typically have pretty strong preferences in terms of what kind of fasteners they want to use. Guessing at what that is before the installer's hired for the job is sometimes challenging. And so you have to balance their preferences and capabilities against the project requirements or the design requirements. Like I said, the welds are the strongest, but the most expensive. They're going to leave burn marks on the underside of the deck, so they're not so aesthetic. The power action fasteners are clearly the fastest as far as installation goes. From a visual perspective, you might see a little bit of point underneath the deck, but normally not that intrusive. Screws might leave a little bit longer point behind, but again, it's on the structural support, so generally might not be that bothersome from an aesthetic perspective. There's some differences that come about based on regional differences that occur in the market simply because of product availability. Different products are available in different parts of the states, and those products that impact the availability of different products impacts the connection choices, the connection options that we have. And sometimes the language that we use can have the same meaning or different meaning to different users based on their perspective. So understanding what some of those differences are will help hopefully avoid some of the confusions that might occur. Some of the things that might qualify as different is the types of deck that are available in a given region, how connection sizes are specified, what kind of design support expectations we have from the design community. I kind of say east-west because the continental divide is kind of a divider relative to where a lot of these differences show up. In areas such as the western U.S., where evaluation reports play a big role in or have a strong influence in the design process, puddle weld sizes have historically been defined based on the effective diameter. So the reports call it a half-inch effective diameter, which is a diameter at the point of fusion with the substrate. That yields a visible diameter in the 3/4 inch size. In other parts of the country, welds are called out. In the eastern part of the country, welds are called out based on visible diameter. So you'll see documents that call for either 5/8 or 3/4 visible puddle welds. Again, differences in how things are described. In the eastern United States, nested deck is commonly available from all manufacturers for the typical 1.5 and 3-inch roof deck products. You can get interlocking deck from at least some of those manufacturers, but it's not the common or standard product used in the eastern United States. In the western United States, about your only choice is going to be interlocking B-deck or roof deck. The interlocking side lap allows the development of stronger side lap connections, which is used to help address the higher diaphragm requirements that the seismic regions bring into play. The arc seam weld shown on the right-hand side of the screen here is the weld that you would use to attach the deck to the structure on either side of a interlocking side lap, where you don't have sufficient space to put a properly sized round arc spot weld. Neither one of these welds, just for to add some complexity, neither one of these welds is AWS pre-qualified, so you have to have the WPSs and PQRs for these welds. Thickness of the structural supports has a big impact on the selection of the fasteners. And it's important to ensure that the fastener that's picked is appropriate for the support member thickness. So coordinating the fastener selection and the cord thickness specifications can become pretty important. It's certainly beneficial to have some conversation about that at the early part of the project, and it may be more economical to specify a uniform cord thickness or define the range of thickness that's going to be acceptable for the top cords prior to the start of construction, as opposed to waiting until the stuff's out on the job site. This is a particularly specific issue for power actuated fasteners that are relatively sensitive to the thickness of the top cord. The different pins, different fasteners have different different capacities, and in fact, in the Hilti, one of the Hilti pins, the tensile capacity changes within the application range of that particular fastener. So understanding what you're looking at as far as cord thicknesses is important. The chart kind of shows the maximal weld or attachment or thickness ranges. The welds I show, the lower bound there that's kind of a skill-based thing. You probably want to avoid getting welds on that kind of material. Screws for supports, SDI defines those as number 12 or number 14 screws. The drill point or the tex, we used to call them tex screws. Now the drill points are selected based on the substrate thickness that you're drilling through. Hilti offers two different power actuated fasteners for deck attachment. The HSN 24 is kind of commonly called their bar joist nail or bar joist pin, and the ENP 19 larger diameter fasteners used for structural steel or heavier cord angles. The HSN 24 is the one I was talking about that the tensile capacity varies within that range of applications, so it's important to understand what that is. NewTek offers 4 different diameters, 6 different fasteners based on, again, the substrate thickness and the thickness of the number of layers of deck that you're attaching with that pin. The NewTek fasteners in particular, you can see have relatively tight application ranges, and in some cases little to no overlap between those ranges, so the importance of understanding the cord thickness before you get out in the field is kind of critical. I've seen shop drawings and photographs from projects particularly with NewTek, that had 4 different pins in every bay. So every joist had a different color of paint on it, so they tried to get the right pin in the right place, but I'm glad I wasn't the guy inspecting. We can use all the fasteners we just talked about to attach concrete-filled deck to the structure. There's also some other options as well. We all know what shear studs are used for as far as beams go and lateral load transfer for diaphragms. They can be used to increase the slab capacity for composite deck. If the report or the data that you're looking at from either SDI or the manufacturer accounts for that, but they're not required for that. When shear studs are being used for whatever reason, if they occur in the same place where an arc spot weld is specified, they can replace that arc spot weld. You don't have to replace the weld. There are some proprietary fasteners for accomplishing shear connection. The Hilti shear anchor that's shown in the middle there. There's also the Volcraft shear flex fastener. The weld washer shown at the bottom, that's typically used in non-composite deck. I don't know if we even carry them anymore, but I think they're probably still used a little bit. Weld washers are not to be used unless the deck is less than 22 gauge. That's in accordance with, in fact, everybody agrees on this one. AWS, AISI, and SDI all say the same thing. Don't use them if it's, unless it's thinner than 22 gauge. So like Tim said, we have to do assessment questions. So, which deck connection types are appropriate for attaching to open web joist? Power actuated fasteners, screws, welds, all the above? It's an easy one. Yes, all the above. So any one of these fasteners could be applicable, but they're not all applicable in every situation. Again, it depends on the choices that have been made relative to the support material. We got the deck attached now to the structure. Now let's start looking at the side laps. Again, this is where regional differences come into play. Interlocking deck, commonly available in the western United States. Nested deck, commonly available in the eastern United States. Each type uses different, or offers different options as far as making side lap connections. The drawing in the middle illustrates that you can, in fact, screw interlocking deck together if you extend the female leg and provide a place for the screw to go in so that it's not having to go sideways through the side or through the lap. Nested decks give us realistically two choices. We can use screws or we can use welds. The welds are either fillet welds or arc seam welds, depending on the amount of material in the lap. Welds are expensive. They're hard to do. They're not very pretty looking from the underside. STI specifically says not to weld 22 gauge nested decks. Screws are clearly more economical. Far and away the most common fastener choice, at least in the eastern United States. The two pictures of the joints, it may not be clear there, but one screw is going into the at an angle into the corner, one's going straight down. I'd say that either one of those is acceptable in accordance. The current standards don't dictate any differences between those. So and is assuming this, of course, that you're getting edge distance. So I would guess that it's kind of dealer choice as far as the installer goes. Actually, last year when we were here, we sat down with the two different guys selling screw guns that install these kind of screws, and one vendor told us to put them straight down, and the other one told us to put it in the corner. And when we showed each of them the other way to do it, they said, "Oh yeah, that works too." So, take your pick. Interlocking decks offer us more choices in terms of the types of connectors. Button punches are the least expensive. They're extremely fast to put in. Typically, they're done with a hand-operated tool. In the western United States, they used to use pneumatically operated button punch tools a lot. Maybe that was because of the heavier gauge decks that are used there. Maybe they're just, I don't know, but I don't know if they were used frequently in the East. They provide limited diaphragm strength. They're typically used in floor deck or composite decks. They provide enough attachment to prevent differential displacement of the two sheets during concrete, the construction process and concrete placement. There isn't really an easy way to tell if you got a good button punch or not, except to have somebody stand next to it and see if it holds together. Screws, like I said before, the screw, this you can kind of maybe see a little bit better that the material on that joint has been pulled from the male leg over to the female side. That happens during the roll forming process. That allows the screw to be installed, at least in the West. If you want to use screws in interlocking deck, you need to tell the manufacturer before he starts to make the deck and ship it to the job site. That's not a choice you get to change out in the field. The reality of it is, as far as in the western U.S., screwed interlocking deck is really not very common. In the eastern U.S., some of the composite decks are offered with a joint that has a full height male leg in there, as well as the turnout on the female, so you can choose between a button punch or a screw when you get out to the job site. Again, that's not something that I would assume. That's something that I would verify with your supplier if that's something that's of interest to the installer. The weld shown here is a top seam weld, or I should say it's commonly referred to as a top seam weld. Recently we got that actually listed in AISI, and being AISI we had to add more words, so now it's called an arc top seam weld. Fabricating or making that weld, you crimp it first with basically a button punch tool without the button in it, and then you weld it. It will leave smoke or residue on the underside of the deck that does not scrub off. It will be there for you to see. It's clearly the most expensive of the connections, but it's also the single strongest connection if you look at the connections in isolation. This connection was the go-to connection of choice in the western U.S. for many years, basically because of the diaphragm requirements due to the seismic conditions. The clinched connections shown at the right, that's a proprietary connection. The manufacturers provide tools that provide some kind of a piercing and deforming action that creates a definitive material interlock in the connection, as opposed to a button punch that's just a dimple but doesn't pierce the material in any way. The one shown here is the Verco punch lock system, but there's other alternatives in the market. Once those were introduced into the market, the use of the top seam welds is pretty well diminished. These go in basically as fast as a button punch does, but give you the capacity, not quite individually the same as a weld, but in system capacity, it's equivalent to the weld, to the systems you get using top seam welds. I apologize, the top, just above the black line, there's the green line that shows the strength of the top seam weld. And at the very bottom is the blue button punch. This comparison basically shows why the market has almost exclusively shifted away from top seam welds to the mechanical or clinched connections in the western U.S. where the diaphragm requirements are so high. So we talked about aesthetics some, understanding whether aesthetics are going to matter in your project is important, and it might impact the choices you make for the connections. Clearly, welds, particularly as you can see here, the top seam welds leave a nice mark on the underside. In thinner decks, they might, particularly nested decks, if you're welding, you could have holes in addition to the marks. Screws you're going to see sticking down below the bottom flange if you're using screws at your nested side laps. So the question is the deck going to be left exposed to view after the project is done? Are we going to field paint it and cover that up? Are we going to use, what kind of lights are we going to use? Are they going to be lights that highlight the imperfections in the deck, or are they going to be ones that hide it in shadow? So if aesthetics is important, button punches and the mechanical clinches are going to give you the least visible appearance from the underside, or the most attractive appearance from the underside. And in mechanical fastener, the pins at the supports are probably the simplest connection, or the least obtrusive connection from that side. So we talked about the different fasteners and some of the details. Talk about how those are distributed around the diaphragm or around the deck. The choice of support fasteners is usually it's governed by, you want to use you want to use the least number of fasteners possible to resist either the wind uplift or the diaphragm requirements, depending on which is governing your design. This picture illustrates the common patterns that are used for 1.5 B deck. Like I said, B deck's far and away the dominant product as far as roof deck across the United States. In parts in the eastern U.S. where diaphragm's not that high, but wind uplift is looked at. My experience is that a 36-4 pattern is a good starting point. Oftentimes that'll meet your wind requirements. It almost always meets the diaphragm requirements. In the western United States, The 36-7 pattern's traditionally been the go-to pattern simply because, again, you've got higher diaphragm requirements and you've got to get, you need to meet that with more fasteners. Some of the intermediate patterns like the 36-5 was used for years when we started zoning diaphragms. Another choice to consider is to look at a pattern that uses a 7 pattern at each at the end of every sheet, and a 4 pattern at the intermediate supports between the ends of the sheets. This pattern gives you the strength and the stiffness. I won't say fully the 36-7, but in the high 90% of the 36-7 pattern at a cost of a 36-5 pattern in terms of the number of fasteners. So it's a more economical solution. Some manufacturers tabulate information related to this. If it's not tabulated, it's definable in accordance with the SDI diaphragm procedures, so it's a solvable, it can be solved by your supplier. There's another area where words can have 2 different meanings. The terms that we use to describe the attachment pattern at a perpendicular support, 36-7, 36-4, are the same whether we're talking about nested deck or interlocking deck, but they have different meanings to the installer. As you can see, the interlocking deck requires 2 welds, one on either side of that side lap. In a nested deck, one weld is expected to attach both sheets to the structure, so you've got one less weld. So same words, different meanings. The definition of side laps, the side lap connections, or how many side lap connections we're going to use. Again, there's different ways that this is addressed in the market. 2 in particular. One is to address the create tables based on the number of side lap fasteners per span. This is far and away the most common practice in Eastern deck manufacturers' literature, as well as in all the SDI publications. Depending on how broad you want to have your range of options, it can lead to some fairly large tables. At least that's what I've run into when trying to do it in the West. What you see commonly in the West is the other alternative, which is you specify the spacing of the side lap fasteners in feet or inches. And that lets you create smaller tables that cover a broad range of it gives you the most options. The challenge then is you want to make sure that you provide a path to get to the number of fasteners in each span, so that you have a whole number of fasteners in each span, which is what you want. So you'll see diagrams and tables like that in the literature to help communicate that to the installer. Talk briefly about a few of the applications and some implications that they have on the decks or the connection selection as well. When we look at deck wind uplift, we need to check the deck for bending and deflection. We need to check the connections for pure uplift. Those checks are done based on the components and cladding wind forces. When we talk about diaphragms, there's a whole lot of factors that affect the capacity of a diaphragm system. We've talked about the support connections and the side lap connections and the different choices of patterns and spacings and types. In addition to that, the deck profile, the deck gauge, the deck span, and the number of spans all have an impact as well. So again, that's where manufacturers' literature and design tools come in, because they help take that, what seems like a gigantic forest of things, and break it down to something fairly simple. I mean, what this slide is illustrating, that any one of those individual fasteners in the deck system, there's multiple forces. You've got axial forces, you've got tensile forces, you've got shear forces acting on each of those fasteners. When fasteners are subjected to significant tension due to wind uplift, that essentially that creates a reduction in the available shear capacity that those fasteners have due to the shear and tension interaction. Now, historically, this isn't something that deck tables or deck literature has addressed in the past, but recent changes in SDI recommendations or guidance have led to the development at SDI of a brand new deck design manual for deck attached to cold form framing that the principal author is sitting here in the room, and we have it's available for review at the SDI booth downstairs. In addition to that, there's going to be an online tool that's expected to be launched shortly that's going to support that book that, again, will help make the design of or addressing the interaction that occurs between uplift and shear a simpler, basically trying to simplify it. Some deck manufacturers and fastener manufacturers are also offering literature and design tools that address this condition. But like I said, historically, this is something that's been, most of the literature in market has been quiet about. Final step in the diaphragm design is to ensure that the number of support attachments at the cords, struts, ties, other collectors that are parallel to the deck are adequate to develop the full capacity of the diaphragm. Simple approach to that's how much shear, how strong is the fastener, figure out your spacing. I want to pick up on something that Tim talked about when he showed you all those elements that you can use to put between the top cord of the joist girder and the deck to allow that lateral load transfer to occur, is to make sure that when you're putting that on your drawings that you're specifying that you're only asking for parallel attachment at those places where you're transferring parallel loads in and out of the diaphragm. It's not uncommon to see an expectation that the deck is attached at every parallel element that it crosses, whether or not that's part of the lateral system. That adds expense and cost that has no benefit to the deck, no benefit to the joist, but it does increase cost and expense. Another place where connections come into play is wall anchorage. Steel deck has a relatively large axial capacity, so it's well suited for handling axial loads. It can be used to brace the walls for out-of-plane forces when the deck is perpendicular to the wall. It is not used when the deck is parallel. In that case, the cord or other elements span between the joist or the other framing members, and those members are axially loaded. The deck connections are going to have to be considered for that, though, because they're usually the governing element. Just as a really simple example, if we look at a 35-foot tilt wall, might generate in the range of 1,600 pounds a foot of load at the roof line. In comparison, a 22-gauge B deck, 6-foot span, is going to provide somewhere in the range of 2,400 pounds of capacity per foot, so well within the deck capacity to resist that load. When you look at the connections, a 36/7 weld pattern is going to give you 2,200 pounds, so also comfortable. The larger Hilti fasteners are only going to give you about 1,500 pounds, so now we're starting to run into a little bit of difficulty. So you have to pay attention to that when you're making that choice. One of the things that, and we've started doing some more of this analysis recently and come to realize that maybe by dumb luck more than intent, one of the reasons why we didn't see the wall anchorage problems with steel deck diaphragms in the seismic events in the past in the West is because by the time we got enough connections to get to the diaphragm capacity we needed, it generally meant a 36/7 pattern and puddle welds at the wall. And so whether it was intentionally being done that way or not, we had enough capacity there to provide an adequate anchorage to the wall. One of the things to watch for when we're detailing on open web joist is where do we locate the laps. Roof deck is typically lapped, normally a minimum of 2 inches in order to get reasonable end distance on your fasteners. Composite deck is normally butted because the deformations or embossments that are used to create composite action, make it a little bit harder to lap. When you're making that lap on open web joist, it's usually a good idea to make that occur over a chord angle and not over the center of the joist. If you're going to make a butt joint on open web joist, either make it on both pieces land on one chord angle or ensure that there's an adequate load path from between the chord angles. All right, so we've got the deck down, it's attached. The last thing to talk about here is hanging loads. And I got to say, this constitutes probably one of the more frequently asked questions for the deck manufacturers. The way it typically goes is we get a call from the GC or the mechanical contractor saying, hey, I need to hang this load and I need you to approve it. Well, that's nice, but we didn't design the building, so it's really not appropriate for a material supplier to be approving something like that. The engineers call us and they ask questions like, what can we hang? How much can we hang? Is this a good detail? So let's start by kind of walking from where we were to where we are now in terms of how this is dealt with. Some of you may remember the older guidance that came out of the steel deck industry and the SDI in particular. It was really simple. For roof deck, it was don't hang anything from the deck. It was a nice, easy answer. I love to fall back on it. In the West, it didn't really hold up. They still hung ceilings and other lightweight fixtures from it. I don't know how well enforced it was in the East, but that was the guidance up until maybe 2000-ish. After that, the SDI roof deck standard added language or changed the language that basically said the engineer of record's responsible for looking at the hanging loads in conjunction with the other loads on the structure, what you would expect them to do. Want to particularly, we'll cover some more, we'll touch on this again in a minute, but the last user note there is maybe use some explanation. It talks about a rule of thumb relative to distributing hanging loads when you're on 1.5-inch deck, but that the point I want to make is that that's applicable if you've got some kind of, there's a base plate, there's some other load distribution element that's causing that to happen. If you're just starting with a single screw connection or something like that to the deck that's just a small point load, this note is not addressing that kind of a condition. I wish I could say it was simple, that there's only one choice, but there's lots of choices for hanging stuff from deck. For years and years and years, the thing that people used was the hanger tab shown in the center. That's rolled into the deck during the roll forming process. It's basically just a couple slots are made and the deck is pushed down in between that. Not long after I started in this industry, there was a number of significant failures and lawsuits that came out of that. So some manufacturers, not all, stopped making hanger tabs altogether because they didn't want the liability. Some of them turned the tooling around and now they make vent tabs that look just like upside down hanger tabs. The load limits that you see published for these range anywhere from 25 to, I've seen as high as 100, depending on gauge. Again, that's something that's going to be pretty specific to the manufacturer. In the West, I don't think that there's anybody that makes a hanger tab or offers a hanger tab for to the market. In the East, I know that some manufacturers still offer them. So they are available if you, but I wouldn't assume that they're available all the time. Some of the other options that exist, screws, obviously you can do all kinds of things with screws. This one in particular is a pre-assembled clip that they can fit in a tool and stand on the floor to do it. On the other side, on the left, there's something called a Sammy Express from Buildex. It's kind of like four wings that clamp. Four wings that clamp it from the back and provide a connection. Those kind of sheet metal connections, the Sammy ones have to be tested. Screws can be calculated in accordance with AISI. But the manufacturers will typically, put design information together in evaluation reports or catalogs to make it simple to pick the connections. Last one shown here on this page is a wedge anchor. Again, that's another proprietary type fastener. It's a generic picture, but in reality, these are specific to the deck profile that they're designed to fit in. In order to spread load on top of the deck, sometimes you see rebar with tie wire wrapped around it. You see strut put in there with threaded rod or other fastenings around it. Those do help get a lot more width of deck engaged. They also create a lot of love with the insulation installer. The middle one there is just a large fender washer that's used to hang a threaded rod, but again, that's not really acting as a load distribution device. When it comes to composite decks, it's really not recommended to hang very much at all from the bare deck itself. What you want to do is engage the slab, not just the deck. Some of the cast-in anchor choices include things like the blue banger there that's designed to take threaded rod from below. Pigtails, whether it's a piece of sheet metal strap or twisted wire punched through holes that have been punched in the deck, or a bent threaded rod that again is mounted in some way so that it engages in the slab. Once the concrete's cured and you like silica dust, you can use the drill-in anchors that have been the common go-to anchor in the past. You can also, power actuated fasteners, again, they make pre-assembled clips that can be used with tools from the floor. Dovetail deck, again, the anchors can carry a substantial amount of load, proprietary based on the particular deck profile that they go in. And these pictures here are courtesy. Epic was gracious enough to share a few pictures of some of the projects that they've done that show the versatility of the hanging systems and the variety of things that get hung from the underside of deck. So when you are looking at that connection data from the fastener manufacturer and thinking about making, selecting it for hanging something from the deck, keep in mind that what that information is telling you is it's the capacity of that connection in isolation. It's not telling you the capacity of the deck. You have to take that, evaluate the deck in conjunction with all the other loads that are applied to it. I've seen products offered for market that say it's good for 500 pounds, let's say, and the deck that they're saying it goes in order to do that, you're talking a span 18 inches. So you've got to look at the system in total. Other factors that affect like I said, we talked before about the distribution of load across more than one rib. Deck properties are published typically on a per foot of width of deck. B deck has 6-inch ribs. N deck has 8-inch ribs. If you've got an anchor that's only connecting to one rib, you're probably going to want to adjust your properties to account for that. If you've got a spreader like we showed up there before, and it's still in fact spreading across the deck when it's in use, you can count on more deck. And then again, there's the rule of thumb from the SDI that's applicable if you've got something wider spreading out the load. I love this. Get a call from the engineer. Come out and tell me that the dents in my deck are okay. And you see this. So you can imagine that it was kind of a carefully worded response. All right. So we look at, we've talked about a lot of things, and we started out saying we're going to try and make this simple, and it seems like I probably made it more complicated. There's a lot of resources available that are intended to help make it simpler. The code or the reference standards that the code points to, which would be the SDI roof and floor and non-composite standards, and the AISI S310 and S100 standards, they tell us how to determine or evaluate those connections and how to evaluate the deck systems from those. Deck manufacturers and the SDI put out a lot of literature, design tools, evaluation reports that take that information and try and turn it into, provide it in a way that makes it easy to make those selection options and find the information that you need without having to go through all the hoopla of doing all the calculations and information themselves. reiterate that a lot of the fasteners, the power actuated fasteners, the clinch connections, a lot of the different fasteners we talked about are proprietary in nature, and that means that they have to be tested. And I'm being given the high sign, it's time to go. So, good thing we're on the last slide. So, like I said, tried to make this not necessarily simple, but clarify the issues that are involved so that you know what the issues are and what kinds of things to, or where to go looking for resources to help evaluate these choices. Understand that in any situation, there's probably more than one combination that will get you to the design requirements. And sometimes more fasteners that are quicker to install are going to be less expensive than fewer fasteners that are stronger. Sometimes lighter gauge deck with more fasteners is going to be less expensive than a system with less fasteners. Being flexible and willing to look at multiple alternatives is going to be the best way to get the most economical solution for the customer or for the owner. So I guess with that, the most important question is, what's the PDH code? We'll show that again, and then open up the floor to any questions if there's any questions. All right.
In the interest of time, we can stay after if anybody has questions.
Thank you very much.